All right, welcome back to the second example of shells. And what we've got here is we've got y equals square root of x, and we're going to rotate it around the x-axis, and our boundary is going to be the line x equals 4. So we're going to get a just sort of cone-shaped thing here. And you're looking probably at the page and saying, well, you've already done it. Yes. Didn't use shells, use disks. Yes. Really straightforward and easy. And this is a great example for how do we use shells because we already know what the answer is going to be. Looking at my disks, the radius is equal to the square root of x. The width is equal to delta x, which means that the volume is pi r squared delta x, which is pi x dx. A simple integration tells me that the volume of this shape will be 8 pi. But now let's talk about what happens if I use shells by rotating this rectangle around the x-axis. So, what is my height of my shell? Well, the height of my shell is 4 minus x. Notice that my shell now looks like this. The thickness of my shell is delta y. And what is the circumference of my shell? Well, I'm going to go ahead and I'm going to, well, let's not do it up there. I'm going to unroll my shell. And here we've got 4 minus x. Well, here we have 2 pi r. And what is r? Well, r is the square root of x. So the circumference is 2 times pi times the square root of x. But notice that my variable of integration is going to be dy instead of dx, which means I need this circumference and this height of my the shell, sorry, my unrolled shell, to both be in terms of y. So what is x equal to? Well, x is equal to y squared, which means that this is equal to 4 minus y squared. And square root of x, of course, is therefore equal to, well, we already knew was equal to y, so this becomes 2 pi y. And so now I have that the volume of one shell is equal to 4 minus y squared times 2 pi y times delta y. And I am integrating from 0 all the way up to, well, if y is the square root of x, x is 4 from 0 to 2. Of, here we go, 2 pi multiplying by y, I get 4y minus y cubed dy. The 2 pi comes out front. I take the antiderivative of 4y minus y cubed, which is 2y squared minus 1/4 y to the 4th, evaluated from 0 to 2. I love it when my lower bound is 0 and there's a y in every single one. Just makes life so fun. And doing the math, plugging in the 2, what I end up with is, no surprise at all, 8 pi units cubed. Mr. Armitage, that was really complicated. Why would I do it that way? Well, I wouldn't. I would never, ever do that one using shells, except that it's a great example because we already know the answer, and so we know that we did it correctly. So let's think again about what do we know about the shells. Well, we need the height of the unrolled shell, we need the circumference of the unrolled shell, and we need the thickness of the unrolled shell. And we need to remember that we are integrating, because these shells are lying on their sides, we're integrating in the y direction, which means from A to B in the y direction, not the x direction. All right, my students, go ahead and do exercise 35a out of the book. And when we come back, we will look at one more shell example where we have the difference of a couple functions. Thanks for watching.